Okay, friends, here's a quick run through of the graphing homework that you had over the weekend, which not everybody did. Some people didn't have some time, some people just forgot, maybe lazy, some people just need some reminders. But in any case, if you didn't do it, you should do it because I will collect it and take a look at it. So in any case, the first one had to do with this problem about tree ring growth. And tree rings, as you're probably aware of, is the sequential laying down of every year of a new ring of tree growth. And the interesting thing about it is that the reason we get rings is because in the spring, it when the buds come out and it's warm again, the trees grow very quickly. And in the winter, things slow down a lot. So if you look in our microscope, you see really big cells followed by small cells. And the small cells kind of look like a line from our distance. In fact, if you went to the tropics and cut down a tree, you'd see no growth rings, and the reason for that is just constant growth all the time. So in the tropics, it's actually pretty hard to tell how old a tree is, yet for our trees in our temperate area, you can actually count the lines. The other thing to think about too is the thickness, how they change. And when you have really thick rings like this, it would probably imply very good growth. And here, where it's very narrow, that might imply a drought, insect damage, or even possibly fire can cause those type of things. So the bigger the rings, thicker the rings would imply the faster the growth and probably the healthier the forest was that year. So here's the first set of data, which was you knew the age of the trees, but you didn't know what the thickness of the growth rings would be. And there's two different forests, forest A and forest B. So therefore, the first question about dependent independent variables, the one that you know beforehand, the independent variable would be the age, and the dependent variable would be how thick the growth rings are. So again, the dependent variable would be the tree ring thickness, and the age of the tree would be the independent variable. And here's just another picture, and again, that you can, if I was to count out here, 1, 2, 3, 4, 5, well, I think it's about 10 or 11 years because there's 10 or 11 rings there. So I did the graph, and this is what the graph looks like. Again, x-axis independent variable, y-axis dependent variable. Notice that I have a title. Notice that, which some people forgot to put on. I also have the units here, which are years, and here I have the thickness, which also has units in millimeters. And we've got kind of two straight lines going on here, but you notice that forest B tends to be higher every time than forest A. Okay, what is the average thickness of the annual rings for a 40-year-old tree in forest A? So in forest A, here's 40. Well, actually, here's 40 years, and here's forest A. And if I was to, I don't see any data points, so you know it's going to be between here and here. So the easiest way to do this would be to kind of draw a line up at 40, and then go over to the y-axis. And there's, as I go over the y-axis, you can see there's 35, there's 40. So I would guess it might be somewhere around 37 millimeters. Obviously, it's going to be bigger than this point and somewhere below that point. And so you're looking at information between your data points. So the answer here is 37. Next question is, what do you call it when you make predictions within your data? And that is called interpolation. Kind of got cut off there, but interpolation. What was the mean thickness of annual rings for all trees found in forest B? Well, if we go back to your data, and mean is another way of saying average. So what is the average of these set of numbers? Add them all up and divide by 6, and you should get some type of number. And that number, I believe, was 36.8 millimeters. Next question said something like, based on the data, what can be concluded about the comparative health of forest A and B? And again, if you think about the fact that big growth is better than smaller growth, would imply probably a healthier situation, then I would probably assume then that forest B has better growth, so it must be healthier. And again, if I either look at the graph or I go back to my data here, there's 20, it's 24 there, it's 24, 28. It's always a little bit larger in forest B, so that might mean that they had better soil, better light conditions, something along the line to make it a healthier situation. And then the last question on this data was, what type of relationship was this? And then you go to that first page, there's direct, indirect, and different types of things. And sometimes there can be no relationship. But as one goes up, the other goes up, as you can see here. And this is actually a direct relationship. As one value goes up, the other one goes up. But to be honest, most trees would probably go up a little bit and then kind of level off and go up and down around a certain kind of thing. I'm not sure about that, but based on the way this data is presented, not my data, it would definitely be direct. And I'm assuming some of you did not, in fact I looked, didn't do the second practice problem. I'm not going to go through all the questions, but the quick setup was that we're seeing what effect does water temperature have on the number of developing clams. You can control the water temperature, that's an independent variable, but you don't know how it's going to affect the number that develop. And so if you were to graph this, which I did, so you can at least take a peek at what it should look like, is it water temperature on the x-axis, independent, number of developing clams on the y, tidal, those type of things. And it looked to me that at 30 degrees or something above 30 degrees is where it tends to do very well. So that's it. Make sure that you do those questions and finish them up, because I will probably grade this now since you can do this. This is stuff you can do.